Kids, hey, we are going to go through a double slit practice problem. Now, I realize the words here are kind of small. I'll read it out loud, and then we're going to work it out together. So it says, two parallel slits are illuminated by light composed of two wavelengths. So let's actually draw this just so we have it. So I'm going to, all right, there's my two slits, okay? Two different wavelengths, one which is 486 nanometers, probably 486 nanometers is probably blue or blue violet-ish, that color. So I'm going to say blue. So there's one of the wavelengths. On the viewing screen, the wavelength who is known, so this one, produces a third order minimum. All right, so let's draw that. So here's my screen, and this blue light, now remember, the blue light hits here, okay? So that means my starting condition for the blue light is in phase. Why? Because the waves making the interference pattern are coming from here, and those waves are hitting there at the same time. They're the same wave, so therefore I start in phase, okay? And then my ending condition, okay, here would be my 0th maximum, but my first min, first max, second min, second max, third min, so it would be first, second, and then my third minimum would be here. I don't know if you can see that, sorry. Okay, but actually I'll do it below so you guys can see it. So first max would be here, second max would be here. This would be the first min, second min, third minimum here. So that's where I'm going to. This is my third minimum, okay? So that's my picture. So for this light, ending condition is out of phase. Therefore, for this one, my path difference has to be, remember, this is 0, this would be 1, this would be 2. So that means this is 2.5 waves, okay? So hopefully that makes sense, because this would be a half, 1, 1.5, 2, 2.5, that's where I'm going. So again, all I'm doing, I'm reading the problem, and as I read it, I'm drawing my picture, writing down stuff I know. All right, so let's go back to the problem. On the viewing screen, the light who produced a third over minimum. All right, so we're there. At the same place where the light it makes an unknown, the light whose wavelength is unknown, it produces a 4th order bright fringe. Now, it's going to be a different color because it's a different wavelength. I'm going to go with red because that's what I have. We'll see if it actually is red, but it's going to, so again, this one starts in phase and it's going to end in phase. So for the red, my starting condition will be in phase. My end condition is going to be in phase. My path difference, if it's the 4th order bright fringe, is going to be 4 waves, okay? The fringes are counted relative to the central maximum, okay? What is the unknown wavelength? So we're trying to find this one, which I'm guessing is red. We'll figure it out if it actually is red, okay? So let's set up our equation. So then you would set up your equation. You go, okay, well, in this case, okay, I know that D for the blue, I'll use blue. I know that D sine theta has to be equal to 2.5 times the wavelength. And my wavelength is 486 times, actually I'll just do nanometers. I'll just leave it in 486 because then my final answer would be nanometers. If I was doing it in meters, I'd have to multiply times 10 to the minus 9th, but I don't have to. And then for my red one, I would get D sine theta. Again, remember, it's the same angle because we're looking at that angle. It's going to be the same for both of them. equals 4 times this. And then it's like, well, wait a second. D, that's the same. It's the same angle. So then I just have to set this equal to this. And if you do that, so let's do that. And so I'm going to get 2.5 times 486 equals 4 times theta, or lambda. And then you can solve for lambda. And let me get my calculator and do the math. Okay. 2.5 times 486 divided by 4, and you get 303. So I am completely wrong, which I should have known because it's a bigger distance, but that's okay. 303 nanometers, which is probably not even visible. It's actually not even visible anymore. So this is more like an ultraviolet, but that's okay, wavelength. So hopefully that makes sense. There you go. All right. Bye, kids.